Hello everyone and welcome to Outokumpu webinar. My name is Outi and I will be the moderator for this webinar. And this is the second of our 4 webinars regarding bridges. One moment, I naturally have a slide issue. Now it's working, yeah. Okay, so first of all, I would like to remind everyone that this webinar will be recorded. The recording will be shared to you after this event, and we will also publish it later on our website. So we have a total of 4 bridge-related webinars that we are organizing, and this is the number 2. So in case you missed the first one, so please visit our website, and you can find a link to the recording and you can watch the first webinar. We talked about pedestrian bridges and presented a few designs all over the world. If you have any questions, please use the chat. You can find it on the right-hand side of the screen. The questions will be presented at the end of the webinar in our Q&A session, and I will be presenting them. And if there are so many questions that we don't have time to answer them, then we will answer you personally through email. Today we have 2 speakers. They are both located in the UK. First, we will start with our keynote speaker, Nancy Baddoo, who is an associate director at the Steel Construction Institute. And she will talk about how to design a stainless steel bridge and talk about those technical details and some key points to keep in mind when designing. And after Nancy, the next one will be Andy Backhouse, who is a lead technical manager and our bridge specialist here at Outokumpu. So Andy will then talk about material selection for different environments and especially about Duplex stainless steel. So now I would like to hand over to Nancy Baddoo. So please, Nancy, share your screen and I will close my camera.
Well, good morning, everyone. I'm speaking to you, as Outi said, I'm speaking to you from the UK and I work for the Steel Construction Institute. We are an independent institute that promotes the use of steel in construction in all sectors, and my particular responsibility is high performance steels such as stainless steels and high strength steels. So before we get down to any details of designing in stainless steel, let's start with an overview of structural applications. The purpose of this slide is to show you that stainless steels have a long track record of successful performance in a variety of applications. They may be fairly new to bridges, but they have been used for many, many decades in other sectors. So I've shown on this slide a tank. I've shown structural members in a desalination plant in London. Stainless steels are used for example, beams, columns, platforms, supports in processing plant. All load-bearing members, water treatment, pulp and paper, nuclear, biomass, chemical, pharmaceutical, food and beverage industries. So these are not new materials for load-bearing applications. And as we turn to think about road bridges, railway bridges, pedestrian bridges, we just start knowing that stainless steels are ideal for applications where you need long life, minimal maintenance, and good corrosion resistance. Carbon steel, as you know, has a sharply defined yield point with a plastic yield plateau with some strain hardening later on. That's shown in green. Whereas stainless steels are a little different. They have this gradual yielding behavior with high strain hardening. They're not the only metals, of course, that have these characteristics, but they are a bit different from the carbon steels that we generally use for bridge design. And the non-linearity has some implications on how we design load-bearing members. But the good news is that Young's modulus and the yield strengths are broadly similar to carbon steel. Now on this graph, I've shown the full range stress strain curve. And the purpose of this really is to highlight the very good ductility of stainless steels. You can see that the austenitic family really has exceptional ductility. The duplex stainless steels, similar ductility to carbon steels. Of course, the area under the stress strain curve is proportional to the energy absorption properties. So you can see that stainless steels have excellent energy absorption properties, which is a property that can be useful, for example, in the columns of bridge structures in order to resist high speed impact. The presentation basically is focusing on the duplex stainless steels, which I'd like you to think of as very similar to the S460 carbon steel family we're seeing increasingly used in bridge structures. So similar strengths, 460 megapascals as S460. Of course, austenitic stainless steels are used on bridges, maybe more typically for applications like hand railing. But for the actual load-bearing members, duplex stainless steels are more appropriate. So moving on, I wanted to show you this slide about the low temperature toughness. It's important to have good low temperature toughness for external structures like bridges. And this shows the toughness properties varies depending on the family of stainless steels. And austenitics, you can see quite unusually, they don't even have a clearly defined ductile to brittle transition. And this means they're used in applications where you require very good low temperature toughness. Duplexes do have this transition in a very similar way to carbon steels. Generally, there's very good toughness down to -40 degrees C. There's a little bit of variation amongst the different alloys in the duplex stainless steel family. At the moment, we would advise you to go to the stainless steel producers for detailed information on toughness. But in the second generation Eurocode that we're working on, we are putting in complete guidance in accordance with the Eurocode that gives fracture toughness data, Eurocode 1993-110. So there will be a comprehensive charts there for you to choose the maximum thickness of element, just as you do for carbon steel. So a word on fatigue. The combination of stress concentrations and defects at welded joints leads to these locations being almost invariably more prone to fatigue failure. And tests of a variety of welded joint geometries have shown that austenitic and duplex stainless steels perform very similarly to carbon steels. So the guidance in the Eurocodes is that you can use the Eurocode 1993-19 rules that have been developed for carbon steel. A number of these joint geometries have been tested for stainless steel. So now I want to introduce you to the product standard for stainless steel. This is Eurocode, this is EN 10088, and parts 4 and 5 are harmonized standards, which means that they support the essential requirements of the construction products regulation. And these are the product standards that you specify if you're wanting to use stainless steel. They give chemical composition and the mechanical properties, and also some information on surface finishes. I have summarized in this table the mechanical properties. So the purple row is carbon steel, and then the pale blue row gives you the Duplex stainless steel properties. So you can see why I was talking about, think of S460. Here we have the yield strength, 460 megapascals. Of course, you may be thinking yield strength. Well, you've just showed me that there isn't a clearly defined yield strength. But what is conventionally done for these materials with nonlinear stress strain curves is you use the 0.2% proof strength and call that your yield strength. So whenever you're looking at design standards or guides and it talks about yield strength, it actually means the 0.2% proof strength, and that's what's given in the product standard. So tensile strength of 640 megapascals gives you a tensile to yield strength ratio very similar to carbon steel. Elongation, similar to carbon steel. Young's modulus, similar. And the strength to weight ratio also. What I've put in the middle are the austenitic stainless steel data, and you can see the strength is somewhat lower, but the tensile strength higher, and that's because of the great strain hardening these stainless steels exhibit. And you can see here the tensile to yield ratio is much higher. Let's move on now to look at the physical properties. And you can see that the density, very similar for all the steels. The thermal expansion is very similar, Duplex stainless steel and carbon steel. Although you will notice that austenitic steel does have about a 30% higher thermal expansion. So if you're using carbon steel with austenitic stainless steel, then you do need to take account of differential thermal expansion in design. And then moving on, looking at thermal conductivity, you'll see that the thermal conductivity of the stainless steels are, well, it's about a third the value of carbon steel. So that can be useful in some applications. If you think of what about stainless steel, say in a thermal break situation, low thermal conductivity is very useful. Austenitic stainless steels aren't magnetic, actually, which is surprising, but the Duplex stainless steels are magnetic. What about bolts and fasteners, screws? Well, there's a European product standard that covers them, EN ISO 3506, and we have a brand new revision of it just published this year. And I've put on this slide here some of the different strength properties you can get in your stainless steel fasteners. You can get austenitic and duplex. These red boxes show the new additions to the 2020 standard. So you can get austenitic and duplex, and you designate them A for austenitic, D for duplex, not surprisingly. Then you designate the fastener with a number that relates to the property class. So most commonly, you'd be having an A480 fastener, in my experience. And the property class is 10% of the tensile strength. So your A480 is really just like a grade 8.8 carbon steel bolt in terms of mechanical properties. But you'll see the new version of the standard has now come up with stronger fasteners and a range of duplex fasteners. So that was an introduction really to talk about how to design load-bearing members in stainless steel. And I've put these photos from collaborators, researchers around the world who for the last 30 years have been pushing and pulling and twisting and tearing and beating stainless steel members and fasteners in order to fully understand the structural performance. When it comes to what types of structural members are available on the market, hollow sections are widely available. Cold formed angles, channels are widely available. You can get hot rolled sections, smaller sizes only, and welded eye sections, welded T's, etc. for the larger sections. You'll see on this slide, there's top right, there's a deep plate girder that has been tested for shear buckling. So that might be something more suitable for use in bridge girders. Now, I think most of you attending are based in Europe, so the talk is going to be aligned to what the Eurocodes say. Eurocode 3 is the Eurocode for steel, and part 1.4 of that Eurocode covers stainless steels. As you can see, there are lots of other parts. In fact, even more, I need to update this slide. There are a couple more parts of Eurocode 3 now. But if you don't do Eurocodes, you're not left high and dry. There is a design standard in China. There's design standard in Australia, South Africa, and there's a lot of activity in the States. There's a design standard for cold formed stainless steels, which is being updated and extended. And we're also on the brink of issuing a full AISC design specification for structural stainless steel. So there is a range of design specifications available. So let me tell you a little about Eurocode 3 Part 1.4. So it covers all types of members, whether you've got bar, cold formed, hot rolled, welded, extruded. It covers the 3 families of stainless steel. It covers ferritics as well as the austenitics and duplexes. And it's quite short because it's only a supplementary standard. So it only gives rules where you can't use the carbon steel rules. And the message I want to convey today is that generally you can use the carbon steel rules. Structural performance of stainless steel is very similar to carbon steel, and it's just some cases where you need to modify coefficients or put in an additional rule because of the high ductility of stainless steel. The Eurocode, its scope, not only does it cover member design, it also covers connections, and there is detailed fire resistance design given in another part of Eurocode 3 covering stainless steel in an annex. Of course, for bridge design, you're interested in Eurocode 3 Part 2, and that runs side by side with the stainless Eurocode, but you should use the partial factors. I've got them in the next slide. You should use the partial factors in Eurocode 3 Part 1.4. So I'm showing them on this slide. Sometimes it's confusing, isn't it, when you're using different parts of Eurocode 3 and they have different partial factors. But in all cases, it should be the stainless steel partial factors that are used. So this slide summarizes what I've already said. Same rules for tension members and for restrained beams, but there are some differences when it comes to the section classification limits and the buckling, whether it's local buckling, flexural buckling, or lateral torsional buckling. For example, here we have the section classification limits, and I've put in black the limits for internal compression parts for stainless, and the slightly higher limits for carbon steel. Apart from that, all the carbon steel limits apply. Another example is when you come to effective widths. So here I've shown that for internal compression elements, a slightly different expression is used. That obviously matches up with the limits shown in the previous slide. So let's just think about what would be the impact of the nonlinear stress strain characteristics on the buckling performance of a column. So let's think about the low slenderness end, first of all. This is where the columns reach the squash load, and the benefits of the strain hardening are apparent. And in this case, stainless steel would behave at least as well as a carbon steel column. Now, shooting down to the high slenderness end, here you've got a low axial strength, the stresses are low, and you're in the linear region of the stress strain curve. And again, stainless steel behaves similarly to carbon steel, providing all other things are the same. So it's really in the intermediate slenderness range where the average stress in the column is between the limits of proportionality and the 0.2% permanent offset strain. That's where you expect different behavior, and a stainless steel column will actually be less strong than a carbon steel column. And so the expressions for column buckling, although they follow the same overall, they follow the same equations, the coefficients are actually different to take this into account. So I'm shown here the compression buckling resistant expression NBRD, and you have these reduction factors chi. And in order to calculate chi, you need to consider both the imperfection factor alpha and the plateau length. Now, this is where different coefficients apply for stainless steel, and I've shown here a table which gives these values. So these values depend on the cross-section type, the mode of buckling, the fabrication process. Now this table was based on tests done, well, really more than 20 years ago, And more recent work has shown that this does need a bit of updating in some places. So very soon, a revision to the stainless Eurocode, a very small amendment, is going to be published. I think it's going to be in the next few months, coming out to the national standards bodies with an update to this table that reflects the fact that the pool of data we have now is so much larger than what was originally used to derive these buckling curves. And finally, on buckling, exactly the same as for column buckling, stainless steel requires the use of different buckling curves, which are defined by the alpha LT and the plateau length. So these values are different for stainless steel compared to carbon steel. Now you're probably thinking about deflections given the shape of the stress strain curve. And yes, because the stress strain curve is non-linear, there will be a reduction in stiffness as stress increases, and you would expect slightly greater deflections in stainless steel. The standard approach is to use what's called the secant modulus that's shown in this diagram in order to calculate the deflection. So you take the secant modulus for the maximum stress in the member at the serviceability limit state. And the calculation of the secant modulus depends on this factor n, which tells you how nonlinear the stress strain curve is. So if you have a low value of n, it's very nonlinear. And if you have a, well, I think if n's infinity, then it's like carbon steel with a sharply defined yield point. However, this is not a particularly significant issue for duplex stainless steels. So you'll find even for heavily loaded duplex beams that there is only a small increase in deflection. It is greater in austenitic stainless steels because of the lower strength. So in the last 5 minutes, I'm going to mention a little bit about connections and then execution. So it's pretty easy. Generally, designing bolted connections in stainless steel will be the same as for carbon steel. One or two differences in terms of the bearing resistance because of this very high ductility for the austenitic stainless steels. Just a couple of things I wanted to flag up, and one is that you do have to make sure that the corrosion resistance of the fastener you choose should be at least equivalent to the corrosion resistance of the material being joined. That's important to ensure a long-lasting, durable connection. And secondly, this issue of galling I want to mention. It's not just a stainless problem. Other metals like aluminium and titanium do gall also. It's when you're tightening a fastener and you have this local adhesion, rupture of the surface. Sometimes it's called cold welding. So you should follow guidelines to reduce the likelihood of galling, slowing down the installation speed, making sure the threads are smooth and clean as possible, and the use of appropriate lubrication. On bridges, preloaded bolts are often used, and indeed on the stainless bridges that we heard about last week, or 2 weeks ago, preloaded bolts had been used. There aren't design rules at the moment, but these have been studied in quite a lot of detail. And the conclusions show that, yep, you can preload austenitic and duplex stainless steel bolts, but you do need to make sure that you're using the right tightening method and lubrication. And the loss in preload is similar really to what you would get in carbon steel bolted assembly. And we have produced guidance on slip factors for grit blasted and other types of stainless steel finishes. At the moment, we're in the process of introducing these design rules in what will be the next version of Eurocode 3, which I think you probably know that the whole of the Eurocode suite of standards is being updated to second generation, and in the next 3-4 years they will all be published. So we will have rules for preloaded bolts there, and we're writing a technical specification with guidance on the tightening method and suitability. What about welded connections? Well, the design rules for carbon steel more or less apply here. You have to use this beta W factor of 1 for stainless steels unless you can justify a lower value. Again, it is very important that compatible consumables are used, and the properties of the filler metal must be at least as good as those of the parent metal. So by that I mean strength, elongation, and Sharpie V-notch toughness. It's very important that suitably qualified welders are used, and when it comes to duplex, certainly greater control of temperatures, etc., is needed to achieve a good joint, and there's lots of guidance on that available. We're commonly asked, can you weld stainless steel to carbon steel? And yes, of course you can, because rarely would you have an entire stainless steel structure. You would always be connecting to carbon steel at some stage. So yes, you can weld them. You need to be careful with the choice of filler metal, that it's over alloyed to ensure that you get good mechanical properties and corrosion resistance. And if you're in an environment with chloride ions or other corrosive environment, then it's important that the paint system that you already have on the carbon steel needs to extend over the weld and onto the stainless steel up to a distance of about 75 mil. I've talked about the European product standard, EN 10088. I've talked about the European design standard, that's the Eurocode. So in my closing couple of slides, I wanted to complete the trio and mention the European regulation on fabrication and installation, which I'm sure you know is EN 1090. And EN 1090 Part 2 gives the technical requirements, and the good news is that it covers stainless steel as well as carbon steel. The stainless steel rules are fully integrated into this standard, so there's not a separate annex or anything. And it gives acceptable standards for the full range of activities, joining, cutting, shaping, etc., etc. This is quite a long specification. You'll know if you've used it. So at SCI, we extracted the stainless bits and we put them into a separate publication. There, I've got it bottom right, just explaining where the rules were for stainless and why you needed them, and giving you some background references on if you needed to find out more. I guess if I would say one thing about fabricating and installing stainless steel, it should be that it's important to avoid contamination of the stainless steel with iron particles from carbon steel, because these iron particles get embedded in the surface of stainless steel, and then it rains and they rust, and you think, my stainless steel is rusting, and then you have to clean it off and it's absolutely fine. But to avoid that process of having to clean it off, it is much better to avoid the contamination in the first place. So there are clear rules given in the EN 1090 Part 2 about how you might do that in each stage of the process. Well, in these slides, I hope I've whetted your appetite for designing structural stainless steel, and there is a lot of additional information out there. So I'm closing by introducing you to the design manual for structural stainless steel, now in its 4th edition, which is available in, I can't remember, 9 languages or something, free download. It's accompanied by design examples, by a commentary, by software, by a webinar, etc. And I think why this guide is useful is the Eurocode is just supplementary rules, so it's a kind of it's a bit difficult to use, but the design manual tells the story from the beginning to the end, and it includes all the rules you need for designing a beam or a column. And I'll also show you this. This is, we've called it an online information centre for stainless steel and construction, but it includes a wider range of resources that might be useful, say if you're welding duplex stainless steels and you're wanting to know what guidance is out there. It will point you to some other resources from other organisations. And I would just like to finish really by summarising that stainless steels have a long track record of successful performance in load-bearing structures. They have the corrosion resistance needed in aggressive environments, which can make them a cost-effective solution, particularly when maintenance is difficult or where you're wanting a very long design life. The attractive exposed metallic finish also makes them a choice for architectural reasons. Design of stainless steel is very easy, very similar to carbon steel, but a few modifications because of the non-linear stress strain curve. You've got your European product design and fabrication standards are all available with various supporting resources that will help you understand them and apply them. So that completes what I was going to share with you this morning, and we're now going to look at the issue of which alloy is suitable for which environment, and I'm going to hand over to Andy, who's going to talk us through that.
So, good morning, everybody, and thank you very much to Nancy for that very nice, succinct and comprehensive run through the main design rules. So what I'd like to do now is just to go through some of the aspects of selecting which of the family of duplex steels should be chosen for a particular project, and this is usually dependent on the environmental conditions. So first of all, just to remind of a slide that if you joined us a couple of weeks ago, I showed this two weeks ago in our last webinar, and just to show that the duplex grades are a whole family of steels, all with quite high corrosion resistance and high strength, as Nancy had been through. But it's actually quite useful to have some different grades, because Some grades are suitable for more mild and benign environments, and some of them at the higher end, for example, the Duplex 2205 is suitable for very aggressive environments. And I'll concentrate mainly on the 2 Duplex grades that have been used for bridges that we showed plenty of examples of last time. That's LDX 2101 with similar corrosion resistance to 316L, and the more highly alloyed, more corrosion resistant grade Duplex 2205. And how we get the difference in corrosion resistance from a steel making perspective is basically to adjust the alloying element content. So the reason Duplex 2205 has better durability, better corrosion resistance, is that it has a higher chromium content and higher molybdenum content, and this is the main difference to getting the higher corrosion resistance. But also the converse of that, of in LDX 2101 having a lower alloy content, means it still has got pretty good corrosion resistance, but the advantage of using something suited for a less corrosive environment is of course the alloying cost less money. So it's really a practical consideration and a balance between the cost and the performance of the materials. So this table and the chart that I showed in the last slide are quite abstract sort of concepts of referring to corrosion resistance and alloying elements and so on. So what I'd like to do now is sort of bring these more into sort of practical reality and explain how you might go in a practical sense, go about selecting an individual grade. Well, for a stainless steel, there are really only 3 main environmental considerations that need to be taken into account when picking the right grade. And the first, and actually the most important one, is to assess how much salt is around in the atmosphere. So salty atmospheres are aggressive towards most metals, including carbon steels, and in fact are aggressive towards stainless steels too. But often a salty atmosphere actually can be a reason to pick a stainless steel because it does have corrosion resistance. The issue with the stainless steel is to select the right one based on the degree of chloride in the atmosphere, which might mean how close are you to a coastal environment, how many kilometers or meters are you away. And even in inland locations, of course, many bridges use de-icing salts, especially on road bridges. So that's another factor that does need to be taken into account. And the amount of salt about tends to be one of the key considerations for selecting a stainless steel. But there are other factors as well, and the amount of pollution in an atmosphere can also affect selection of a stainless steel. So pollution can often give rise to acidic deposits. And although the world's getting generally cleaner, there still are some areas where, for example, in industrial atmospheres or even inside tunnels, where atmospheres can contain high levels of, for example, sulfur dioxide, and that can be an influencing factor. And finally, for a stainless steel, the amount of rainfall, or in a wider sense, the humidity of the atmosphere is quite important. Rainfall is actually beneficial from a stainless steel perspective, especially when there is a salty atmosphere or a polluted atmosphere. Rainfall is really beneficial because it tends to act with a natural cleaning action to clean off all these nasty pollutants. So rainfall is usually a beneficial factor for stainless steel. And the converse also true, that lack of rainfall, especially when coupled with high humidity environments. So I'm thinking of perhaps in the Middle East, in Middle East coastal areas where there is very little rainfall, then the lack of rainfall and the high humidity can actually contribute to the aggressiveness of a coastal environment. So Dubai would be a good example of an area where that factor would need to be taken into consideration. So those are the 3 main considerations, and how best to decide which stainless steel to use where. Well, actually, there is no quick and easy route to be able to quickly determine what works best where. But fortunately, we've done most of the hard work needed through very long-term testing in many different environments. And here I'm just showing a couple of examples of long-term test sites that we have run and do run for many decades now, which aim to study the performance of the full range of stainless steels, including duplex steels, in a variety of different environments. And we look at many different ones. So for example, at the top, we see on a test site that we have on the west coast of Sweden, where yes, it snows a lot, it rains a lot. So it is coastal, but stainless steel benefits from the generally quite wet, rainy and snowy atmosphere. And we can compare and contrast that to areas such as in the Middle East, in Dubai, with similar sort of test sites where samples are exposed for many years to the salty atmosphere and lack of rainfall. And on these test sites, we study not only the steel, but we can also study bolted connections through crevice joints. I think on some of the samples, you can see some bolts attached. Some of the samples we can put weld beads on as well and study the performance of welds. So in this way, this is quite a good way to get very good data and information about long-term performance. And just two examples here, but many more locations, of course, are interesting to be tested, and we do that in offshore, inland, temperate, roadside environments where de-icing salts might be used. So this type of data has been extremely useful to use in helping bridge engineers decide which grade to use. But there's nothing quite like as well with coupling that type of data with what happens in real life. And we're now 20 years into using duplex stainless steels for bridges. We showed some of these examples 2 weeks ago. But the advantage now of having 20 years of experience is there's now some very good information available from existing structures of the performance of stainless steels. So part of what we do as part of our own research and development activities, we periodically revisit many of the bridges that use our material in different parts of the world to be able to look at the performance. So we go to, for example, the Cala Bridge that Juan Sobrino talked about 2 weeks ago, which is in the Mediterranean on the island of Minorca. And we compare and contrast the performance of steel in that environment to inland Spain, inland UK, inland Sweden, and several coastal regions besides. So I think this sort of practical experience coupled with the long-term test data means we've now got a pretty good grasp of what works well and where it works well. And for any potential bridge project, we're always very willing to have a discussion to share the detailed information that we have and to show lots of photos and so on. But you don't need to come to a producer such as ourselves to be able to pick a steel, because a lot of the information, of this detailed information, has now been encapsulated in the Euro code. There is a generalized international standard ISO 9223 for classifying an environment, and this will be familiar to many of you, where you classify an environment based on its aggressiveness from a mild environment C1 up to an aggressive environment C5 or even CX in extreme conditions. And this, of course, can be applied to stainless steels, but it's actually not the best way to do it. And there are two reasons for that. One is that this ISO 9223, the classification isn't based on the corrosion resistance of stainless steel. It's based on classifying environments based on the corrosion resistance of carbon steel or zinc. Stainless steel isn't included. And secondly, the ISO standard doesn't then lead you to a choice of which grade of stainless steel. It can only classify an environment. However, if you're designing a bridge in Europe, now there is actually much better guidance, and this was added as an annex into the Euro code in 2015. And this annex is now a much better and quite sort of simple way for selecting a stainless steel grade for a structural application. And it's a good system because the system is specifically targeted to stainless steel. It's very simple guidance. It's an analysis you could do with actually very little information about the bridge and do it in probably a couple of hours of work in a morning to quickly get to an answer. And the output at the end is actually a recommendation for a suitable grade of stainless steel based on all the risk factors that might be present. And of course you can read that in the Eurocode, but I just thought I would quickly go through how it works. And it works in a very simple way. First of all, it characterizes the environment of a potential bridge by adding together the known risk factors for stainless steel. So you use a very simple lookup table to first of all determine several factors. The first one is F1. What's the exposure to airborne chlorides? And really that means how far are you away from a coast? Which coast are you near to? Or are you inland? And also, is there going to be any use of de-icing salt? And you assign a number to the factor based on a lookup table. And you do a similar thing for factor F2, which is about exposure to pollution. In most of Europe, factor F2 is likely to be 0, especially in coastal areas, because there's very little pollution in coastal areas. But where there is an industrial atmosphere, then you would need to know the typical sulfur dioxide content to be able to input that into this simple model. And finally, then you just have to know, is the structure going to be exposed to rainwashing, which would be a beneficial effect. So you add all these together, the factors together, and all of the factors in this process are negative numbers. So you end up with a corrosion resistance factor that is a negative number and becomes progressively more negative for more corrosive environments. So the factor shown on this table down the left-hand side, you end up with a number that could either be +1 or going down to below -20 for a very aggressive environment. And corrosion resistance factor 1 is actually for indoor environments, so it's very unlikely to be the case for a bridge, which means that you will be for outdoor environments between the second row and the bottom row in some, depending on the location. So the factor on the left-hand side determines the environment, and once you have done that and you have your answer between 1 and -20 or lower, then you can go on to look at what type of stainless steel would be needed, and that's done by grouping the factors together in 5 areas called corrosion resistance classes, which run from 1 to 5. And the stainless steel grades are then tabulated into each of these 5 corrosion resistance classes, which I will show you in the next chart. This is a very simplified version of the table out of the Eurocode. The Eurocode lists, I was checking yesterday, it lists over 30 different grades of stainless steel. And actually it's probably too complicated. You're not going to need to look at all 30, because in the end, for a structural application, experience says that the optimum solution is usually a duplex grade. So you only really need to look at the duplex grades. And when you look into the different classes, you see that the grade LDX 2101 used in many bridges appears in corrosion resistance class 3, the middle class, and it means in this case that LDX 2101 can be used in class 1 for indoor environments, 2, which is typically a mild rural urban environment with very little salt around. Class 3 is typically an area where perhaps some de-icing salt is being used. Perhaps you're a few hundred meters away from a coast. So there is some salt around, but it's not that aggressive. It's a moderately aggressive environment. And then in class 4, if you have a much more aggressive environment, perhaps really at the coast, perhaps very little rain washing, then the higher alloyed grade, Duplex 2205, is typically recommended by this process. So all of the other duplex steels appear, so that I showed earlier on my chart. You can see them if you look it up in the table. And if you come across a very aggressive environment, which will be class 5, there is a duplex steel that could be suitable and is suitable for that type of environment. I have to say that I don't know of a bridge that has yet widely used this steel, mainly because corrosion resistance class 5 has such a high level of aggressivity, adding together lots of salt, a polluted atmosphere, lack of rain washing. It's quite difficult actually to find such an aggressive environment. But if you've got one, then for sure there is a Duplex stainless steel that could be used in that environment. In the table, there are 30 other grades, and you'll find some of the perhaps better known standard austenitic grades, 316L, 304L, they appear as well in the table. But as I said, for most bridge structures, experience says that it's usually one of the Duplex grades that are selected. So that's quite a simple way to be able to get to a quick answer for stainless steel, and that in combination with test data and experience now means we've got a pretty good handle of what works well where. And I just thought I would finish by just giving a short example of how that sort of Eurocode system would work on a practical bridge. This is the latest example of a stainless steel road bridge. It's a bridge actually only opened a few weeks ago in a part of the UK called Cumbria, which is in the northwest of England. So this stainless steel bridge, this is a photo we took last week actually, so a very up-to-date picture, and the full structure is built out of LDX 2101 Duplex stainless steel. And why was this grade selected? Well, this is a road bridge. It's well away from the coastal regions, which means that the amount of salt around really only comes from the use of de-icing salt. But it is a road bridge, and it's definitely very cold, below freezing in Cumbria in the UK in winter, and certainly expected to snow. So for sure, a lot of de-icing salt in winter. And as you can see, parts of this bridge are exposed to rain washing, but there are also parts sheltered by the deck, which means that some parts will be washed by rain and some parts probably not. And when you go through the Eurocode process, that leads you to classifying the environment between about -7 and -9. It puts you in corrosion resistance class 3, and in the simple lookup table that leads you to the choice of Duplex LDX 2101, and that is indeed what this bridge has been built of. And it means that a good choice of material means the bridge looks great today, and it's more or less the first month of its opening, and it was going to look good for sure for many decades to come. So I will finish there. Thank you for listening. Happy to take questions now, or if you want to be in contact for more detailed questions, there's my email address. No problem to be in touch if you want to ask me in anything more detail. So I'll hand back over to Outi now. Thanks for listening.
Thank you, Andy. Just a moment, I will share my screen. So yes, we have a few questions that have arrived, and if you have any questions for the presenters, please write them to the chat. So first question to Nancy. Is there a high thermal expansion coefficient to stainless steel a problem, for example, when joining stainless to carbon steel?
Well, in my presentation, I showed that the thermal expansion of Duplex stainless steel was very, very similar to that of carbon steel, 13 as opposed to 12 times 10 to the -6 per degree centigrade. So that isn't likely to have lead to any significant problems. For the austenitics, yes, it is higher, and I think you just need to take it into account in detailing. I mean, the metals are joined regularly, so it's not an insurmountable barrier, but it's something you need to know about and take into account.
Then to Andy, does the surface finish influence the corrosion resistance of the material?
Yeah, so thanks, Outi. So yeah, that's quite a common question actually that comes up as well too. So from a corrosion resistance perspective, what is crucial is to get, first of all, is to get the right choice of grade. So grade is absolutely critical for making sure the stainless steel is going to work in the right environment. But surface finish can have a secondary effect too, and actually in some of the in the slide I showing our different test sites, we do actually deliberately test different surface finishes just to assess the effect. And I think particularly if you have an architectural feature, then surface finish can be more important, because certainly smoother finishes tend to trap salt less and pollution less readily, and smoother finishes are more readily naturally washed by rain. So it means that a smoother surface finish is generally less susceptible to, say, quite sort of minor, sometimes it's called tea staining, which is quite sort of a superficial discoloration of the surface. So I would say for most bridge applications, probably the type of surface finish in a sort of a standard bridge might be just by perhaps using a finish using bead blasting or sand blasting or something like that. For sure, it would be a good idea, if you are going to blast the finish, to select a blasting medium that will give not too coarse a finish. Yeah, and I think that would be the general recommendation.
Then there is another one for Nancy. Are there any difficulties in welding and fabrication of duplex stainless steel when comparing to the 316L? And is it sufficient to specify EN 1090?
Well, starting with the last question, yes, I mean, for construction in Europe, you have to specify EN 1090, and that in itself points out to the relevant specs regarding welding, ferritics, duplex and austenitics, stainless steels. I think I said for welding duplex, you need tighter controls when it comes to heat input, and I recommend there's a particularly good technical brochure on fabrication of duplex stainless steels produced by the International Molybdenum Association, which goes through all the issues in great detail. Would you like to add, Andy?
Yeah, I was just going to add actually that if there are fabricators on the line who are listening and who need more detailed guidance on welding of stainless steels, then we actually produce our own quite detailed handbook. It's probably more relevant for fabricators because it's quite detailed about how to set up welding heads, heat inputs that you need to apply, joint configuration and so on. And in principle, the same equipment is used for duplex steels as are used for austenitic steels, but a bit like the design codes, there are some differences here and there that it is important to know about. And I said if there are fabricators or projects that fabricators are unfamiliar with welding, then I would say please contact us, and we're quite happy to send out our welding guide.
Okay, I think we are running a bit over time, so I will take one more question. This one is for Andy. Can the Eurocode material selection system be used for bridges outside Europe?
In the Eurocode, I think from memory, there is an explicit sentence that says the Eurocode system should only be used for bridges inside Europe. And the reason for that is, of course, across the world, in general terms, there are many different types of environment that may be quite different from that inside Europe. Asian environments, for example, or as I alluded to, Middle East environments can be very different, and the behavior of stainless steels can be very different. So the principles in the Eurocode, which are assess where the salt is, assess where the pollution is, assess rainfall and humidity. Those principles are valid wherever you are in the world. So the principles can be applied in that sense, but I think for an environment outside Europe, it would be important to take account of the specific sort of non-European type conditions of where the bridge is located.
Okay, thank you. I think we will close now for today. I want to remind everyone about our next webinar in 2 weeks. And in that webinar, we will concentrate on economics, and we will talk about life cycle costs and topics like that. And also Andy will present some very nice cases. But for now, thank you to both of our speakers, Andy and Nancy, for your time. And please, everyone, join us in 2 weeks. Bye-bye.
Bye-bye, everyone.